Dear students, using kinetic theory, we derived expression for pressure exerted by an ideal gas as P is equal to 1 by 3 mn V square, where m is mass of each molecule, where here m is mass of each molecule, n is small n. This is number density. Number density means number of molecules per unit volume. We get that by dividing total number of molecules by total volume occupied. V square bar means mean of the squared velocities of the n molecules. Say this is equation 1. Substituting in place of n, capital N by V. Substituting 2 in 1, we get P is equal to 1 by 3 m n by V square bar. Multiply on both sides by capital V, we get PV is equal to 1 by 3 m n by V square into V. Here V and V gets cancelled. So we get PV is equal to 1 by 3 m n V square bar. Now multiplying numerator and denominator of right hand side by 2. PV is equal to 1 by 3 mn V square. This can be written as, see here, mv square is there. For kinetic energy, the formula is half mv square. Therefore, let us write that half mv square. Half mv square. Let us write the remaining. See these two, this m, this v square written here. So what is remaining? 2 by 3 is remaining, and here capital N is remaining. Capital N is remaining. PV is equal to, say this is third equation. Now let us think about internal energy of an ideal gas. Internal energy of an ideal gas. E is equal to, see, internal energy is a sum of potential energies and kinetic energies. But in an ideal gas, there is no interaction between molecules. Therefore, potential energy becomes zero. Why? Let me write here. In an ideal gas, there is no interaction between molecules. See, the reason is the distance between the molecules is very large. In kinetic theory also we gave assumptions. One of the assumptions is the distance between the molecules is very large. So the force of attraction is negligibly small. Therefore, there is no interaction between molecules except during collision. Only when there is collision between molecules, only then there is interaction. And in other cases, there is no interaction. Therefore, potential energy is zero. The ideal gas will have only the kinetic energy. Kinetic energy of one molecule. If there are n molecules, the total internal energy of the ideal gas becomes n into half mv square. Say this is fourth equation. Now, in place of n into half mv square, you can write E value. So, substituting 4 in 3, we get PV is equal to 2 by 3. In place of this, we write E. 2 by 3 E. This is fifth equation, and this fifth equation gives this equation gives relation between pressure and kinetic energy of ideal gas. Let me write the fifth equation once again. Now, ideal gas equation. Ideal gas equation is PV is equal to mu RT. So both fifth and sixth equations have same LHS. Therefore, RHS can be equated from 5 and 6. You can write 2 by 3 E is equal to mu RT. Say this is seventh equation. But okay, 2 by 3E is equal to mu. So in place of our NA into KB is equal to R, you know very well. The product of Avogadro number and Boltzmann constant is equal to universal gas constant. So in place of universal gas constant, we can write this Na Kb T and 2 by 3 E is equal to. So we defined mu in two different ways previously. One was m by m naught, another was n by Na. Now let us use this. Mu is equal to n by Na. Here Na Kb T. Now Na gets cancelled. So we can write E is equal to, take this 2 by 3 right hand side, it becomes 3 by 2 N Kb T, or take this capital N left side, 3 by 2 kBT. See, E is the total kinetic energy of a given ideal gas and N is total number of molecules. So when you divide total internal energy divided by total number of molecules, you will get average internal energy or average kinetic energy. So this becomes average kinetic energy. This becomes average kinetic energy. E by N becomes average kinetic energy. This is the eighth equation. 3 by 2 is a constant. Kb is a constant. Since this is a constant, taking this as a constant of proportionality, you can write mean kinetic energy is directly proportional to temperature. So average kinetic energy is directly proportional to absolute temperature. Absolute temperature. So it also to see or internal energy. This also can be taken as internal energy. Internal energy. Because ideal gas internal energy means kinetic energy. Therefore, instead of kinetic energy, you can say internal energy. So, average internal energy of an ideal gas depends only on temperature. See, it depends only on temperature. Internal energy of an ideal gas depends only on temperature. It neither depends on pressure nor volume, and it doesn't depend on pressure or volume. So this is very important thing, very important. Internal energy of an ideal gas depends only on temperature. It doesn't depend on pressure or volume.